So do you need me to use this, or can I just project to the back of the room? Can you hear me all the way in the back?
I can.
Fantastic. So that way I can be a little bit mobile. So this talk is called Design Principles. Now, of course, there are so many design principles that we could talk about in the design of software that I picked one. And I think one that's very important, which is talking about complexity, something that we talk about a lot. And I want to dive in. I want to do a few musings on complexity, as it were. So before we get started, we're at PyData DC, hosted at Capital One. It's Sunday, October 9th, 2016, and I'm James Powell. If you like this talk, you can tweet at me at Don't Use This Code on Twitter, or you can send me an email at james@don'tusethiscode.com. Now, one thing that, if you've been to other PyData events, you may have seen talks that I've given, and one thing that I've developed some reputation for in my talks is writing very provocative code. I like to write code to really provoke people, to make them think about things. Thus, the email address and the Twitter handle, Don't Use This Code. It's kind of a disclaimer built into everything I do, just to say, this might be interesting, but I'm not saying that you actually would ever use this. I've given talks about metaclasses and Python features. I've given talks about generators. I've given talks about a project I did called Py3SO2, where I embedded a Python 1 interpreter into a Python 2 into a Python 3, so you could run Python 2 and Python 3 code in the same process, and they could interact with each other. I wrote a little tool called rwatch, where you could add read watches to Python that could just dramatically change the way the interpreter works. This one nobody seemed to really like, but I wrote you can write LD preloads in Python, and it was a real puzzle to try and figure out how to actually link them. But I can write LD preloads in Python, so I was able to write in Python in about 30 lines of code an LD preload, so that any arbitrary program on my computer that was written in C could transparently work with zip files. Without having to know that there were zip files, my LD preload just intercepted open, read, write, and all those other calls to give you unzipped data and then transparently zip it back. I thought that was kind of cool. And in Amsterdam this year, I gave a talk called From Past Import Print Statement, where I added the print statement back into Python 3. You know, it was a fun joke. I'll say that for my talks, they're not all party tricks, but it is true that they are often very self-indulgent. The reason for that is, you know, it's kind of fun. It's kind of fun to see what you can do within a Python interpreter, how you can bend the rules, and how you can bend the rules without quite breaking them. I would say if there's a legitimate reason why I give these talks, it's to kind of explore the space of possibilities behind what you can really do, how you can take your knowledge of Python, your knowledge of CPython, specifically your knowledge of how the C runtime works, and really drive it as far as possible. And my goal in that is to show you some tools to solve actual problems. Now, I'll admit to you that these are problems that you might never ever have. In fact, these may be problems that you might hope to never have, but you might eventually run into, and if that were to happen, it would be nice to be able to solve them. It would be nice to know what exists at the frontiers, at the boundaries of our knowledge, so that on that fateful night, you know, come 3 a.m., you put down your phone, you stop tweeting, because you've gotten that was a political joke? Nobody? Okay, I'll keep the political joke. We're done with political jokes for this year, I guess. But you know, it would be nice to be able to solve some of these very hard problems in as surgical a fashion as possible. And so a consequence of the construction of these talks is that they showed very complex things you could do with Python in order to entertain the audience. That is, the complexity of the solution was directly correlated to how entertaining it was supposed to be. And I never really talked about applicability. You know, would you ever really do this? And I never really talked about justifying the complexity. Does it really make sense to live patch your Python interpreter to add some features as opposed to just making do with what you have? I will say, though, that this question of complexity is one that I see come up constantly. It is an elusive question and a very important question. I would say that this is probably one of the most important questions that we ask ourselves as programmers, that we ask ourselves constantly. The other question would be, how do we determine what constitutes good code and what constitutes bad code? And for those of you who've never seen any of my talks, I can tell you, I already know what good code and bad code is. And I can tell you very simply in the span of 2 slides exactly how you can distinguish between good code and bad code. Simply enough, good code is code I wrote, bad code is code you wrote. And really, it doesn't go any further than that. That's supposed to be pretty provocative, too. The idea there being that oftentimes what we consider to be good code is really just a reflection of our own prejudices. And I think that this happens in the same situation when we have to decide whether or not we want to write complex code. Now, one question you might presume is, based on my prejudices of having indulged in all of this complexity and having done all these weird things in the CPython interpreter, I might be telling you, you should write complex code. You should take the sophistication that I present in these talks and go hog wild with them and add them to production systems. And the don't use this code is really a wink wink type of thing. But it's not. Because I'll tell you right now, I don't think you should write complex code. In fact, I don't think you should even solve complex problems, at least not for money. And I mean that very seriously. Because, as engineers, for us, what's most important is the applicable value of a problem, not how hard it is. In our spare time, when we're at home, when we're having fun, the hardness of a problem might be very satisfying, but it doesn't necessarily drive any value. I work as a consultant, and in many cases, there's a lot of risk in what I can deliver in terms of value to somebody. I'd rather solve the easiest problem I can, because I know I can get it right, and I know I can get a paycheck at the end of the contract. Fundamentally, difficulty of a problem is a risk factor. Complexity is a risk factor that's added to our engineering process. Now, some people would say that complexity is a competitive advantage. It's not. It's not a competitive advantage. And you often hear this come out in many different ways. You'll talk to people and they'll be bragging about the complexity of the problem they're trying to solve, their business model. They'll tell you something like, oh yeah, we're doing this at scale. We're an advertising company, and we have billions of requests per second. It's so difficult. We have to have sub-microsecond response times and things like that. And when you look a little bit closer, you'll see they're guided towards that, not because it was an interesting problem or because it was something they wanted to solve. It's usually because they had to have that level of complexity. They had to have those response times or those number of messages in order to be profitable. And so when I hear people tell me about how difficult how difficult the problems they're trying to solve are, in my mind, it sounds like them saying, let's start an airline, because the margins are really thin, and that's not the kind of business I want to be in. I want to solve easy problems that are very valuable. Solving hard problems can be a competitive strategy. You could talk about complexity capture in the same way that you might talk about regulatory capture. The idea being that you invite complexity into the problem that you're trying to solve in order to engage your opponents on some ground that's not favorable to them. So you can move faster on this ground than they can. You know that you have better programmers than they have. And so you try and trap them in some area where they can't compete. So it's more of a competitive strategy than a competitive advantage. But I would say even then, I find this fairly uncompelling. Because I think difficulty or complexity as a barrier, a competitive barrier in a marketplace, really is a very shallow moat. The reason for that is there's always somebody out there who will fight you by finding a cheaper, easier problem to solve. And I think generally that's what we see in the marketplace. You try and solve a very hard problem. You put a lot of resources in solving that hard problem. You put all your weight behind solving that hard problem. And some small startup solves 80% of that problem much cheaper than you can, and you're outcompeted. This is, of course, part of the reasoning behind this mantra of worse is better. That oftentimes solving the entirety of the problem, that the problem itself is sufficiently negotiable that solving the hardest problem might not actually be as valuable. I would say that I would encourage you, in general, to only solve hard problems where they are disproportionately valuable. Complex problems can sometimes be disproportionately valuable to how complex they are. And those are the problems you want to tackle. So I'm not here to tell you that you should just enjoy complexity just because that's something that I show in my talks. Now, there's still a core question here of when is complexity desirable? Or, in other words, when is complexity justified? And we all have an intuitive answer to this. We've all cursed our way through incredibly complicated code. We've all worked on some project and we said, why on earth did I do it this way? And just cursed from the moment we got access to the repository to the moment we were able to put in our change request or our pull request. And we've also seen this problem from a more quantitative approach. We've heard people talk about lines of code or cyclomatic complexity or, heaven forbid, K-complexity in trying to quantify how complex a piece of code is and say, well, this is a little bit too much by a cyclomatic complexity perspective. But what I'm trying to drive here is a more qualified justification. What qualitative metrics can we use to really try and figure out, are we going off the deep end? And I would argue that the qualitative metrics that we have right now, at least the aphorisms that we have in our industry right now, are exceptionally poor. One of them is a phrase that I absolutely hate. which is keep it simple, stupid. And the moment somebody says to me, keep it simple, stupid, the only thing I can think is, no, you're the stupid one. But I mean this in two ways. The first way is that I often see this phrase used to cover up for deficiencies. Somebody says, keep it simple, stupid, because essentially we all kind of try to code to our own level of competence. So, there's some reason why they don't want to engage a certain degree of complexity, a certain degree of sophistication in the code you write, because that's putting them into unfamiliar territory. And you'll see this in some very interesting ways. I mean, I'm sure you've all talked to somebody who said, oh, version control is a little bit too much. Why can't I just tarball everything? And if you went back 20 or 30 years, you'd hear people say, structured programming? No, that's just fluff. We could just use goto everywhere. And the argument here is that, we all have some barrier for what we consider to be too complex and not complex enough. And to say keep it simple, stupid, because it's just beyond what we know is, I feel, a fairly uncompelling argument. Now, I should qualify that by saying that it's okay not to know something. I'm not diminishing people by saying that if you don't know something, or if you don't have a certain level of technical sophistication, that's wrong. It doesn't diminish you as a human being, and it doesn't diminish you as an effective contributor to a project. What I am saying is, for all of you here in the audience, for every pair of you here in the audience, there exists some level of complexity, some example, such that one of you would say that's too much, and one of you would say, no, that's necessary to solve the problem. We could find a problem where you would say, no, I think that's a little bit too much, let's do it simpler. And Tom Caswell would say, well, you know what, we actually need to do it that way. Or Bobby Fillar would say, no, I actually disagree. And so there's always some distinguishing level of complexity where we're not going to agree. In essence, simplicity is not some uncontested good. And when people say things like keep it simple, stupid, it reminds me of a slogan I heard from a startup. We're all familiar with Facebook's corporate motto, move fast and break things. And I read a blog post a couple years back about a startup that wanted to have their model as move fast and don't break things. And I thought that's absurd, because as though it were so easy, right? I would say a better view of this is if we look at the Zen of Python. We see that 2 lines of the Zen of Python address this head on. They say simple is better than complex, and complex is better than complicated. And the essence here is that simple isn't something, we can't just write simple code as though it were something that we could just do. There's always going to be some reason why there's complexity in our code, and what we're trying to avoid is not complexity, but complication. And I think the Zen of Python tries to tease out that a little bit more. I'd say the second reason why I don't like keep it simple, stupid, is that I think it's only valuable as a statement that you say to yourself. I told you, no, you're the stupid one. Well, that's the truth. When you're saying keep it simple, stupid, that's something you're saying to yourself. You're calling yourself stupid because you're trying to say, let's not get carried away. Because we all know that when we're working on a project, there's some degree of self-indulgence. We get so wrapped up in solving the problem that we might try something just to scratch that itch that maybe isn't that valuable to anybody in an organization. I would say that fundamentally what distinguishes writing code as an engineer versus writing code as a software programmer is that engineering fundamentally is work subordinated to some process. When you write code as an engineer, you're subordinating yourself to some goals of some organization. So maybe it's not the code that you want to write. Maybe it's not code that's interesting to you intellectually. But the satisfaction you get is from serving the needs of the organization, not serving your intellectual needs. But I'd say the question still remains. How do we distinguish between something that is unnecessarily complex and something that is irreducibly complex? And I want to give you an example from a talk that I gave a long, long time ago. One of the most maligned features in the Python languages, metaclasses. This is a feature where I've seen very talented Python developers give talks saying, don't use metaclasses, they're too confusing, they're too complicated, they don't do anything, they're a stupid approach, don't use them. And people who should know better. Now, I will argue that if you have a straw man example that looks something like this, then you're 100% right. This is a metaclass that swaps the order of derivation, so a base class and a derived class get swapped. This is absolutely and totally unnecessary. The problem it solves, I don't even know for certain that it would solve the problem that it's supposed to solve, and heaven forbid, I can't even understand what I looked over that when I looked at the code, and I can't even understand how it works. It's just beyond the pale. That said, what I would argue for you is that for each of the mechanisms that were introduced to a programming language like Python, there's generally a reason for that. And if you dig deep enough, you might find what that reason is. These mechanisms are merely tools to accomplish some goal. In the case of a meta class, I would say that there's actually a fairly clear goal for what they accomplish. Meta classes are our tool in Python for enforcing constraints from a base class to a derived class. Dead stop. And almost every justifiable application of that is enforcing constraint from a base class to a derived class. What do I mean? Well, we have two classes. We have a base class and we have a derived class. Base and derived, right? If we want a constraint that goes from the derived class to the base class, for example, we want to say our derived class asserts that the base class has a doIt method, then we might have some code in some file that has class base, and we can't touch that file. We don't even know where it is. And we have in some other file our derived class. And in our derived class, we put a little assert at the top, and we say assert that that base class has some attribute, so that in our code, when we call run it, we know that the doIt was implemented by the base class. And if it wasn't, then this code would never compile in Python. It would never get past the module evaluation step because the assert would trigger. Now, that's not actually true because asserts are not a runtime checking mechanism in Python, because if you do -o, the asserts are disabled. So if you wanted to add a little bit of perhaps unnecessary complexity, you really should do it like this with a has-adder check and raising your own type error. But the idea being that if you in a derived class want to make sure that the base class has some properties on it, you can do that because you put that code right next to where you write the derived class. And fundamentally in this example, you're the one writing the derived class and somebody else has written the base class. How do you do it the other way around? How do you have your base class enforce a constraint on the derived class? How do you write some code and then say everybody who needs to derive from this has to follow some rules? Meta classes are basically the only mechanism to do that. So in this example, you have some base class that has some runIt method that calls some doIt method. You don't implement it. You're enforcing that everybody else implements it. This is some kind of interface pattern or abstract method pattern. And in fact, if you look at Python, in the ABC meta library, they have the ability to mark abstract methods on Python instance methods. And it just uses a meta class construction a little bit more sophisticated than the one I'm going to show you. So in some other file, you have your derived class, and you can't touch the original file. So all you do is you add some meta class, and it says, whenever I'm constructing a new type, I just make sure that new type has a doIt method, and if it doesn't, I raise a type error. And then you add that to your base class, and everything that derives from a type which has a meta class on it derives that meta class. So the base class has to have a doIt method, and I set it to none. This is a almost ridiculous equivalence to setting a virtual method in C++ to 0. How preposterous is that? And the derived class necessarily has to have a doIt method, otherwise the Python constructor won't construct that class. And there are actually 2 or 3 other mechanisms to do the same thing in Python. There's build class, there's init subclass. In Python 2, there's one other mechanism. But fundamentally, what you can see is there's a goal that we have. We have some code that has some constraint that it needs to enforce, and this is the only mechanism that we have to do that via code. So when you come to me and you say, I don't like meta classes, I saw a talk by so-and-so, and I was told don't ever use them, they're too complicated, and you say, I don't want to use meta classes, then I'm going to say, fine, you don't want to use them, you're going to end up using them in one way or the other, or you're going to end up doing something much worse. Because when you want to make that, when you want to enforce that constraint, for example, in a real situation I saw where we had a unit testing suite, and in that unit testing suite, we had to set up a test DB in all of the unit tests that we wrote. And in order to set up the test DB, we had to call super setup. And a bunch of people were forgetting to call super setup, and their unit tests were writing against a production database. Or they were failing because they weren't initializing some special fields for the database. And somebody said, well, we need to make sure in everybody's unit tests, they call super setup in their setup method. Well, there's a common base class, and that base class needs to make sure in all the derived class that everybody else writes, the super setup method is called. That's exactly the pattern that we're looking for. And so this is how you solve it. And so I spent 30 minutes. I wrote them a 25-line meta class that would do it. And I said, this is the solution. And they said, I don't want to use it. I saw a presentation. It's a bad idea. And instead, they wrote something that looks like this. They wrote a little bit of code that used regular expressions to parse every file in our system and send an email to people where it didn't seem to have a super setup line under a setup line under a test line. And it was about 1,000 lines of code long, and it sent out a lot of emails, and it required a lot of change requests, and there was still some stuff that slipped through the cracks, but they said, I think this is a better approach. And we could argue whether it's a better approach or a worse approach, because maybe I'm wrong. Maybe I'll argue that the code is much shorter in my example, and it's much safer, and it works, but they might argue that Sending emails gets you some visibility, so it's good to let the boss know that you're working. And it's obvious for a newbie to look at. The meta class might be a little bit too much for if this were a task that a junior programmer were working on. It might be a little bit too far beyond what we could expect of them. And so I'll admit I might be wrong. But in this presentation, one of my goals is to avoid giving you really boring answers. Boring answers like qualified judgment is, it depends. Or qualified judgment means it's a series of trade-offs. I hate these answers because they don't say anything. So what I want to give you in the last portion of this presentation is a very simple framework that I use to determine where complexity can be applied. This framework doesn't work in all circumstances, but I found that it can sometimes help me justify decisions that I make about, is this too much or not? It's based on the idea that we can quantify things in a very fuzzy fashion, just thinking of budgets. So we have a complexity budget. Our project has a budget that says, here's some complexity that we're willing to spend as part of this. And there's generally two considerations for whether we want to, how big that budget should be. One is, how sophisticated are our users? Do we want to optimize our code for a junior programmer, for a newbie? Does it make sense to optimize our code for newbies when there's 3 newbies and there's 3 junior programmers and 100 senior programmers? Does it make sense that we to optimize our code for newbies when we have 3 newbies, but in 6 months' time they'll be up to speed? Should we really optimize our code for those 6 months when somebody just joins the organization, not the 12 years when they stay here? And those are all reasonable considerations. One example that I'll tell you that you can see this in is CPython. If you ever look at the Python interpreter, you can see that it's intentionally written to avoid fancy constructions in C. It's intentionally written to be hacked on by fairly junior C programmers. In fact, I can promise you, after this presentation, within 25 minutes of time, I could get every single one of you in this room up to speed on how to hack on CPython, and all you need is a C compiler on your computer, and you need to be able to read through like an if statement and a switch statement, and that's it. CPython is written to be hacked on by amateurs, and as a consequence, it is a very flexible interpreter that has a lot of contributors. It's a very low bar for contributors, and so you have a very active CPython contribution. I believe the number that I last saw was 1,692 total contributors to CPython over the last 26 years. So it's a very low bar, and it works exceptionally well for that project. The other consideration for setting this complexity budget, I think, is how much do your users really care? Do they care about the code, or do they just care about the results? And what is your expectation for them to learn about this artifact that you've created, this code that you've created? And I think if you return to Python, you can see this as well. When Python first emerged as a language 25 or 26 years ago, people naturally are not going to care about it that much. They're going to see it as a tool that accomplishes some work, but they're not going to spend all of their time learning about it because from a perspective of, I want to learn tools that are useful for me professionally, an up-and-coming tool isn't quite there yet. And so a lot of choices that were made in the original design of Python were choices to, let's not rock the boat too much. Let's just rely on defaults provided by the operating system. Let's not build our own layers of systems. Let's not add any crazy features that people would be mystified by. And as the project grows over time, in the ensuing 25 or 26 years, there is more of an incentive for people to care about how Python works, for them to really sit down and understand the language. And so there's greater budget for the language itself to develop complexity in terms of fancy features like async I/O, async await generators, and so forth. I like to think of this as if we graph these two things on axes, how much the users care and how much they're expected to know, how sophisticated they're expected to be. We end up at the top axis kind of saying, are we talking about smart users or dumb users? And are we talking about users who care or don't care about their code? I will fix this a little bit, though, because I don't want to imply that knowing something means you're smart and not knowing something means you're dumb, because I think that's a pretty offensive thing to say. Additionally, I don't want to imply that don't caring about a tool means you don't want to use it. It just means you don't want to learn. You don't want to go out of your way to bend yourself to that tool in order to make use of it. So I'll change my graph a little bit, and we'll talk about sophisticated versus users who are developing sophistication. Or to keep it small, we'll just have it like that. So you can think of the D as whatever you want, but if we want to be polite to our friends, it's those who are developing sophistication, are users who are not expected to be expert programmers, expert data scientists, expert at the field we're looking at. And I'll show you a couple of quick case studies just to show how I've used this framework. One case study is stylistic complexity. So we often see cases where you could write code looking like this. You have some modality, and you encode that modality in your function using an if, just using some control flow structure. And somebody else comes in and says, well, instead of control flow structures, we could use a dictionary, because that's kind of our switch equivalent in Python. And somebody else comes in here and says, well, we could use functional programming instead, and that's even fancier. And all three of these pieces of code accomplish the exact same thing, but there is some justification you need to say is which one is best. How should we write the code? If somebody disagrees with the way the code's written, how do we litigate that disagreement? And if we go back to our diagram, we can think, well, if we're down this last column of users who aren't particularly sophisticated, then obviously we probably want the first approach. If we're talking about people in a corporate training situation, and I've done a lot of corporate training, you don't want to use the last two options because you'll lose them right out the gate. You want to use a simple option that's closest to what they already know. And if you're on the other column, then you're a little bit freer to use whatever stylistic complexity you want because you can assume their users are just going to breeze by that. It's not going to stop them. Similarly, if you think about dynamic complexity, and this is a problem that we run into in Python a lot. We have enormous tools for metaprogramming. We have macro systems in Python. We have all sorts of ways to add some distance between the actual code mechanism that exists at runtime and the source text that we've written. Meta classes are one example, but you can think simply in Python, you can have a for loop, and in that for loop, you can add things to your local dictionary, so you can programmatically define functions in a for loop in a module. People don't generally do that because certainly library authors don't do that because they expect to have code contributors, and that's a little bit weird. But there is the ability to add some distance here. And the argument for adding that distance is the fewer physical artifacts, the fewer lines of code I have to write, the fewer things I have to fix if I need to make a small change. I don't like to repeat myself, perhaps. And additionally, I get to have central points where I can add functionality that goes across all of these fairly similar use cases. So when we think about this, do we want to minimize physical artifacts? And we go back to our diagram. We can see if we're looking at the bottom row of our diagram, the users who don't care about our project, we can see something quite stunning, which is a user who doesn't care about your tool, but only cares about using your tool, is not going to use anything more than the standard tools that they have to understand your code. They won't learn your custom tools. They won't learn your custom build system. They'll learn it only insofar as building your tool so they can use it. And so if they want to make a one-line change, they're not going to jump through 20 pages of documentation to make a one-line change. They're going to use tools and techniques that they already know in order to make that change. And you can see if you ever use any projects that come out of Google, they have enormous complexity to their build system. And for some of us who don't want to be Node engineers but need to use Node, I don't really want to learn Google's build system to build Node because I don't care that much about Node. It's just one component in my system. And I care more about the data science that I'm doing and then piping through a server that I'm building than how the server is built and how it's constructed. And if you look at the tools that I'm going to use, they're almost all static tools. They almost all operate on source text. Basically, I'm talking about grep. Your users are going to grep for a line which seems to be the change they want to make. If they can't find it, they're going to get frustrated. And so when you talk about should I employ metaprogramming, one of the considerations is I lose artifacts on disk that somebody can just grep for, and I lose the ability for contributors who don't fundamentally care to learn about my architecture to contribute to this. And so writing this the dumb way, writing it out, repeating yourself, cutting and pasting the code can actually be much better because you'll have contributors who can actually get a foothold in that. Now, if we look at our diagram and we look at the bottom left corner, if we talk about users who are smart, users who are sophisticated, but they don't care about your tool, you can hedge that a little bit. And you can talk about something, I like to say the principle of importability, which is in a Python module, any Python module that has some runtime mechanisms, those mechanisms should exist on import. So I should be able to sit and say import this module, and I can look into that module dynamically and see all of the mechanisms that I'd use. There shouldn't be some additional registration, initialization step, because that's not what I'm going to do. If I want to understand how a tool works, and it's a little bit more sophisticated, I'm going to interact with it as a sophisticated user using tools I know in Python, using my interactive console, and I'm going to import that module and use dir and help. And so instead of grep, I'll use dir, and I might even write fancy things like little list comprehensions that look through the module contents to find things that I want. And as a sophisticated user, that's what I do. But I'm still going to be fairly reliant on a degree of staticness that you may not want as a module author because you want to use some fancy techniques to minimize the amount of typing you have to do. I want to look at one more case study, which is self-indulgence, because this is a fantastic thing. We all love to write code that makes us feel smarter. Oftentimes, it's an opportunity to make you feel dumber, and then smarter, and then dumber, and then smarter again. So it's a great exercise for your ego. If we look at our diagram, and we look at the top right corner, users who really care about our tool and are also very sophisticated, this is an incredibly fertile ground for us for random experimentation. This is a ground where we can do whatever we want and we'll still get co-contributors. So you could see a lot of JavaScript tools seem to be like this. A lot of JavaScript frameworks seem to be in this zone. They are incredibly complex, and the users are assumed to be very sophisticated, and there seems to be no barrier to how complex they can be with somebody still, banging down the door to learn it. If we were to look at the opposite corner of this quadrant, users who aren't very sophisticated and who don't care about this tool, this is something that we actually end up seeing very frequently in the tools that we have to build. Because this is basically every tool that we build for a semi-technical user. A user who cares about the results, but doesn't care about the process. This is a user that's happy a tool exists, but they don't care it's your tool. They'll use whatever tool gets their job done, but they don't care if it's your tool. They don't care if you did it in some fancy fashion. They don't care if you added a new abstraction. In fact, they would prefer that you not be a pioneer. You know how you can tell a pioneer? By the arrows in his back. I thought that was pretty good. The idea being that these users, you may find some fantastic way to solve the problem. Your users will not care. They will not be willing to learn your new technique because they just want the result. They don't care about the process that it took. And this is an enormous number of tools that we use. A lot of command line tools are this way. I would say even some visualization libraries are this way. One marker of this is when you find that your users refuse to use anything but code they cut and paste from blog posts from 10 years ago. I'm looking at you, Tom Caswell from Matplotlib. It's a very common thing that we see, just getting your users to care enough to actually keep up to date with the documentation and use modern techniques and to use the code as you're currently developing it. So the question comes down to, where is my code? Where does it sit in these quadrants? And you might even say that for different users, it may sit in different quadrants. One example came up when trying to organize a tutorial for a PyData event earlier this year, where we had somebody who gave a stats model tutorial, and they complained about giving a stats model tutorial. They said it went horribly because we needed the people in the audience to know something about statistics. I'd rather give a scikit-learn tutorial because you don't really need to know anything about machine learning to use scikit-learn. And that was a very provocative statement, I thought. And you can think that the scikit-learn developers certainly would not agree with that. But there are a lot of statistical users who think, well, the API is so simple, we don't really need to know anything to use this tool. And you can see that in that case, that tool is actually used by users in very, very distinct quadrants. So you do have to prioritize. You have to understand who are the users you sufficiently care about, which of those quadrants do the users you care about sit in. You have to determine from that, what is your complexity budget? And that can guide you in how much complexity can be applied. You may, in the process, discover that the problem is not solvable, or at least it's not solvable with the current budget for complexity, in which case you might be able to find, or you might be motivated to find an easier problem to solve that gets you most of the way there. You might also find that the problem is too hard for an easy answer. But in general, what you're trying to do is find some justified reasoning for where you apply complexity. What do I use to justify in a qualitative fashion whether this is too complex or not complex enough? So we don't fall back on these absolutely poor aphorisms like keep it simple, stupid, that aren't anything but a personal attack against people who write code that doesn't look exactly like the code that we write. But we're actually making a solid engineering judgment that serves the task that our work is subordinated to. This is what I call a qualified judgment. And this is one simple framework that I use for actually trying to figure out all these things that I talk about in my different PyData presentations. Would I ever use them in real life? Well, this is part of my judgment. I want to thank all of you very much. I really enjoyed this talk. I'm James Powell. Do we have time for questions? No?
We have 5 minutes.
We have 5 minutes for questions? Anybody?
Give such a compelling presentation.
No questions? Nobody? Was that too provocative? I think one very important thing I want before I answer the question is, I mean, yeah, I say smart and dumb, and that's trying to rile you up a little bit. But really, it is very important to say that if you're on a team with somebody and you're an expert Python programmer and they're not an expert Python programmer, it does not diminish them as a contributor to the project or as a human being to not be an expert Python programmer. I think that we see this attitude implicitly too much in our industry. It's okay to not know something. Whether it's okay to not want to know something, I think that's fine too. Some things I just don't care about. But you know, we're all trying to solve a problem, and as long as we keep our eye on the problem we're trying to solve, that's what's more important. There was a question.
Yeah. What would you say your biggest stocks fall?
Oh, so I had 3 people come up to me at this event say, oh yeah, I saw you give a talk at SciPy or PyData New York or something else, and I really liked it. And I said, oh, which talk was that? And they said, I can't remember. So that should probably give you an idea of where it falls. It's way off the axis.
So read watch, for instance, is that unnecessarily complex or reducible?
Oh, so it is unnecessarily complex because all the things that it solves, you could just throw human labor at, and probably. So that's the thing. A lot of these things, the justification is: do I want to have one person come up with a really smart solution, or I used to work at a big bank. Do I want to have 150 people and a $20 million budget to solve the same problem? And for the bank, $20 million is not really that much money, and wasting 150 people's lives and times and energy and youth, they don't care. I mean, it's part of the metric that they have. For other ones, that doesn't make sense. For read watches, that was just me trying to provoke the audience. Yes.
Spend time for the newbies versus for experienced developers, especially in half a year, those newbies will be.
Absolutely, right?
But it's actually not like that. It's a constant stream, right?
Yes, it is.
So
yes, it is.
it's not like
well, at some companies, it's.
You have only experienced developers. No, you still don't have the same 5, 6 newbies.
That's true. But if you have 5 or 6 newbies out of 100 people, and they're only newbies for 6 months, if you told them just don't look at this project until you're 6 months in, is that really a big deal? I mean, it's part of the question you have to answer. And I think that if you have, obviously, you're not going to go to a company and say, well, I have some newbies and they only know Windows, so let's just throw all this Linux garbage out the door and this Docker garbage because they can't figure it out. Because what will happen at that organization is someone will say, no, the rest of us have been using this for 5 years and the newbies will figure it out, right? Or let's not use Git because they didn't learn it in school. You'd never say that in an organization, right? You'd say they'll figure it out. And that's a fairly reasonable thing to say in an organization. At the same time, you might not want to say, well, Python's kind of passé, and Scala is something that people have actually heard about, so let's use some language nobody's ever heard about that nobody uses just because it's fancy. That's a horrible idea, because how are you going to hire people to actually be effective in your team in a short period of time? So the argument can go both ways, right?
Works actually to advantage. Let's try something new so you can put it on your resume.
Absolutely. I just didn't mention this in this talk because I was seeing how you can be good for your organization. But a great way to spend complexity is we're talking about budgets, right? The situation with all budgets is you have a certain budget of money and you spend it judiciously until the end of the year, and then you gotta spend it, right? So same with the software project. You have some complexity budget, and you make this a little bit complex here, a little bit complex here, a little bit complex here. You have a little bit of complexity left over. Not for the end of the year, but when you see the layoffs are coming, you just go hog wild at something, do the craziest thing you can, pad your resume, and bounce. And it's pretty much the same thing, right? That's career advice. You heard it right here. And yet we've all seen or lived it, I'm sure. Yes, Tom.
Because I would say that of your talks, this is the least provocative of them.
This is the least provocative?
Yes. This may be because I've seen a lot of your other talks, and this kind of crystallizes a lot of the things you've been talking about and disrupting my mind with. But
so where is Matplotlib? As a core developer for a project that almost everybody in this room probably uses on a fairly frequent basis, how do you just decide whether you need to do something fancy in Matplotlib or do it the dumb way?
layers.
Layers? So you have a core of really smart stuff and then
Yeah.
layers of dumb stuff on top?
Yeah. And some layers and how much code duplication it's going to produce.
Okay.
Like, so for 1.5, we added a decorator to basically every function in the library that implements custom keyword argument handling. So if you pass in a data card, and then you pass strings and other variables, it'll look those strings up in the dictionary to pull the values out. That was the code for that is probably like 100 lines of pretty complex code because we're looking at arguments saying, are you a string? Is this in the list of things that are allowed to be looked up? And if you put that on every 4-line function, our code base would have quadrupled in size.
Did anyone say, whoa, that's too much, let's just cut and paste and call it a day?
I mean, when we started down the decorator route, we did have the discussion, but then when we saw what the code required to do that keyword argument handling was, and the payoff for that was a tremendous, if people know about it, a tremendous easing of what users have to write. They can write string A, string B, data equals df, and just get the plot they want. We're willing to accept the complexity of a decorator on all of our functions that hides 100 lines of really nasty code to make that work.
Okay.
So I guess you just kind of have to accept that on these big libraries you have people who can do this stuff.
You have some people in that top quadrant and some people and a majority of people in the.
And I guess it also goes back to your the support into a purpose, right? The purpose is to make the plotting side easy for the users, which means we have to absorb a fair amount of complexity in the back sometimes.
Absolutely. Well, thank you, Tom. It was my pleasure giving this presentation, and let's hear it for our next speaker. Are you-